In this video, I will show you how to calculate IR, which is the current flowing through the resonance tank. Now, in order to do this, we need to simplify the LLC. So we're doing kind of like a first harmonic approximation, where we just take out the resonance tank. So in order to find IR, we need to look at the voltage loop here. So V1 equals VL, which is the voltage over the inductance, plus Vm plus Vc, which is the voltage over the capacitance. So plus Vm plus Vc. So we will first look at only the first half cycle. So during that first half cycle, V1 is constant. However, VL, Vm, and Vc is not constant. So this equation needs to be represented by IR. So the current, so the voltage VL could be represented as LR as IR, because S is just the derivative. And then plus Vm is just Vm, because that comes from the output, as you see here. So it's just N times V out. But I'll just continue writing Vm. And then we have Vc, which is 1 over CR, and then the integral of the current, which is just 1 over S, IR. And when we take the integral, we also need to have the initial condition. So we need to add Vc 0. So we have IR in this term and this term, so we can just solve for IR. That leaves us with IR, and then LR multiplied by S plus 1 over CR S, and this equals V1 minus Vm, this is not constant, so Vm, and minus VCO. And here I forgot, in Laplace domain, you need to divide the constants with an S. So here, V1 over S, and then also Vm. Then we can divide both sides with this term. Then we get IR equals this part, and then divided by this part. So we'll just do it under, and then divide here. Now if you multiply this S in here, this one will be removed, and then this one would be squared. So then we just remove this. And then we can take LR out, such that we have S squared alone. And then we get LR here, and then we remove LR there. So the Laplace transformation of the sine wave equals omega over S squared plus omega squared, which is pretty similar to this. So if we go back to the time domain, you will still have this front, but because we want to get an omega on top, this part will change a little bit. So we get LR over CR squared. I will not explain why. And then we have the sine, and then omega R multiplied by T. So omega R equals 1 over CR LR, and then squared. So this is the equation that we get for IR. This is not the only one that we have, because there are different scenarios. So I'll come back to the second one later. So now we want to find the current flowing through LM, which is simply this voltage integrated. So IM equals 1 over LM multiplied by the integral of Vm. So if we draw these two curves, we can see what happens. So IR is sinusoidal, and IM is increasing. So if they start at the same point, they will meet at one point before the cycle ends, because the half cycle ends here, and then it starts here. And then we'll actually continue like this because we just mirror because the second half cycle is just the first one mirrored. Now, but what happens when they meet? So when they meet, we can see that the current flowing here equals IR minus IM, which is at this point 0. So there will be no current flowing through the diodes, which means that it would be an open circuit. So VM would no longer be defined by the output voltage. It will solely be defined by the current flowing through LM. So VM is no longer constant, and therefore this equation here will not hold, because this assumes that VM is constant. I'm sorry, but this one was wrong. So it should be CR over LR, basically the opposite. So now we want to find the current in the second scenario. So now we will have an open circuit here, which means that we don't have any parallel anymore. So we just have a series between these. So we can look at this inductor as a part of this inductor. So we can assume that these two inductors are just one inductor. So then it would be a lot simpler because we just have one inductor and we don't have VM anymore. So if we just copy this, because it would be quite similar, we can just remove VM, and then we need to just add LM to both the LRs. So this would be the current for the second condition. So we have just LR plus LM here and LR plus LM here as well. So we just need a parenthesis like that. So the current can now be written as one function where it's this one for when IR is not equal to IM, but when it's equal to IM, we get this function. So here we have omega 2, which is this one, and here we have omega r, which is this one. Now, one disclaimer, this function is wrong. It's not correct, because LM is not included in the first one, and it's dependent on LM. And the output resistance is not included either. So it needs to be wrong. But like the only thing that is wrong is the gain and also omega r. So if you just increase or decrease, so if you just increase omega r, you will get the correct waveform. I tried to simulate in Plex and compare it to this function, and it got quite similar if you just corrected the omega r and also scaled the amplitude of the current. So by plotting the current waveform, we will get 3 different types of waveforms. So when the switching frequency of the MOSFETs are equal to the resonance frequency, we will get a sinusoidal waveform of the IR. And IM will just go up and down. So here the voltage is always constant for each half cycle. So the half cycle will stop here. And then when the switching frequency is lower than the resonance frequency, we will get a waveform that looks like this for the current. The reason why it looks like this is that for the first part of the half cycle, we follow this equation because IR is not equal to IM. So IM would be equal to IR at the same point as for the resonance frequency one. However, the period is not yet done. So at this point, there becomes an open circuit in the diode bridge, which means that we follow this waveform. Now, the reason why I just put it flat, it's actually not flat. I just put it flat because omega 2 is lower than omega r. And we also have this factor, which is lower than this factor. And this factor is also lower than this factor. So just because it will increase so little, I just set it flat. And it's not a bad approximation. And then when we have a frequency higher than the resonance frequency, we will get a waveform that looks like this. So for this example, the switching frequency is about twice as large as the resonance frequency. So when we reach about a quarter of the period, this primary bridge switches, which means that we start a new response. So we will still use this equation, however it will be mirrored. So we'll just add a minus sign in front, because now we have a new half cycle. So during the first part of the second half cycle, this bridge has not yet switched because it's switching when the current is 0 because they are diodes. So they will not switch before IR equals IM because the current flowing through here is proportional to IR minus IM. So when this is 0. So there will actually be a phase shift between the primary bridge and the secondary bridge because the primary bridge switches here and the secondary bridge switches when it meets here. So we will get a fast decrease during this time period. And then at this point, we start a new step response as for the first half cycle.